can do it. So I think this is the hope there, and that's with a former student now, an assistant professor at, in Pittsburgh, Antonella Palmassi. But again, many groups do that, and it's very impressive what the LIGO people, LIGO Virgo people manage to do. And I know there's activity in India in this field, and there'll be a new device here. So I think it's something to look forward to. Okay, and then here we try to give the buyer's guide to the Hubble constant. Okay, so in a kind of traffic light coding. So for example, if we look at Cepheids, right? So the color coding is green is kind of, it has to do with, the astrophysical modeling, do we trust it, photometric reduction, calibration, and population size, right? So that's not too bad, this green population size for Cepheids. Red doesn't mean it's wrong, it's just you need more work. So yes, you would like in gravitational waves to have the population bigger, right? Things like that. So, these things which can, will be with us for many, many years, and each line here could be a PhD project, if even more. Now, I want just to tell you about two surveys which I happen to be involved in over many years, especially DES. After I moved from Cambridge to UCL, we got involved into that with many institutions. The lead laboratory is Fermilab, and this is already the optical correctors for both, by the way, we built in our basement. Both are old telescopes, but which got some new life through new instrumentation. So it's also very interesting how one can extend the life of observatories. Each of them is 4 meters. One is in Chile, this one, and the other is in Arizona. And there's basically, the camera is still there, but it finished already observations. But I have to say, maybe it sounds a bit embarrassing, but analysis is still going on. So it's just the finishing the observations, it's not the end of the survey. And DESI just started, but 2020 already measured 12 million spectra, which is about a third of the expected ones. And these 12 million by DESI are more spectra than ever collected by humanity before. Okay, so it's really a jump there. And each survey, there's more and more people, and so on and so forth. And for DES, we actually created a book. We thought it's good to document the story, because at the end, you just see technical papers. You don't know why was it done, why did people think that way, who did what, especially in instrumentation. Very important to give credit to the instrumentation people. So you can look at it. It's a multi-author book. And then supernova, well, again, just to show, this is still the latest from DES, but very soon there'll be year 5. But again, Bob can tell you more stories, but essentially this is this residual is, against redshift. So when I was a student in Cambridge, PhD student, we were told that this is the real universe, okay, the blue line. And what the supernova teams have shown, that is actually different universe with this omega m of 0.3, omega lambda of 0.7, and that's what comes from DES, right? So that you can see that you get interesting information there. And if you remember my slide, it's an interesting period where you have the transition from matter to dark energy. You have the acceleration and then the equality. So it's very important to get those points. So this, very soon, there will be year 5, okay, of this supernova result. Now, in terms of large-scale structure, what became popular is to combine large-scale structure and weak lensing. Here, the big achievement, it's 100 million galaxies with shape measurements. So I hope you appreciate that, okay? And it's very difficult because I saw how the optical corrector was built in our basement. And to think that after all that, where you have to polish things to 60 microns, the width of human hair, you can actually measure these things. I think it's a big achievement also to the instrumentation people. And it's when you combine them that you get this result that I showed earlier, minus 1.03, but you have to read the fine print because, for example, I'll focus on that. This is omega matter, and this is the clumpiness amplitude called S8. And you can see that actually what you get from Planck, which is the green, and what you get from DES, lensing plus large-scale structure, those two mountains don't quite overlap. They don't quite overlap. And some people just, and remember, this is a two-dimensional projection. So one has to be quite careful. Are you allowed to combine it or not, you know? And some people just do it, and others develop some techniques. A former postdoc, Lemos, devised a statistic called suspiciousness. So if you want to look at that suspiciousness, which is a way of telling whether or not you're allowed to combine. So, you know, when I tell you it's -1 to 3%, do read the fine print. It's far more complicated than that. And now we enter to the big data, and the story here is really whatever you want to do, you know, just the data are going to be enormous. There's no way you can do things without some kind of machine learning. You can see jumping from 1 terabyte for DES to 1 petabyte in SKA, and this is only a subset of projects, right? And I'm sure you know Euclid will fly actually in July, if all goes well, on SpaceX, rather than on the Russian rocket. And Rubin LSST, we heard the other day in the talk, maybe some first images in early 2025. Lots of data, you know, billions of galaxies, billions of dollars. We like to tell the funding agencies it's only $1 per galaxy, so it's okay. And someone else the other day made the remark that, you know, you can almost give each person on the planet a galaxy or two. It's about that number of people, is it? Yeah. So this is all interesting. Now, also, there's no time to talk about it, but I want to emphasize that service also found the unexpected. Great attractor, BAO, etc. And now, really, I left it to the end about this machine learning coming into it, and my take on this is that it's not artificial intelligence, it's augmented intelligence. We should use the human knowledge and the laws of physics. And we've seen different diagrams yesterday. Each person had their own statistic on archive, but either way, I looked at the number of deep learning titles, and you can see from 2017, it goes up and down. Maybe it's going down, start getting down, because it started getting a bit boring to put that same title. You know, for my sins, we did some work in the early 90s on classifying galaxies. We had some gurus at the time. And for those not familiar, and I know there are many practitioners here, and there's some very nice presentations yesterday at the end of the day, but people here. But the shift has been, the reason for this jump is that you go from first extracting features of the object and then feeding it into a neural network or decision tree, or you show the whole image. And my point here is that actually shallow learning is not so shallow because there's actually human knowledge that went into it. People have thought what the different features. So I'm actually maybe a bit old-fashioned here, but I think there's a room for combination there. And there are different ways this works. I mean, we have, you know, different techniques. We can just do all the work instead of on 1,000 objects on 1 billion. But I think we're still waiting for some big revolution. So I wasn't sure, is it evolution, revolution? So I went to ChatGPT, and it's very diplomatic, more diplomatic than me. So it said that it has the potential of being both, it said. And at the end it said, you know, it has the potential of fundamentally changing the way cosmologists approach and study the universe. I would say we're still waiting for the killer application. Like in protein folding, it really changed the field. I'm not an expert, but that's what people say. But you know, there is activity there in DES. For example, you have already 12 papers that use machine learning for things from finding dwarf galaxies to trans-Neptunian objects to multi-messenger, ghosting, and so on. And this is an example we discussed yesterday, and some people here I know are working on it. So they came to talk to me about this. It's for LSST. This is simulations, and with arcs due to strong lensing, and these are without lensing. And you know, this algorithm managed to find them rather well. 90%. Okay, it doesn't get it always correct. I mean, this is a difficult one, right? You don't see it, at least by eye. So that's one direction. Photometric redshifts, I've been looking at it for 20 years. The idea is you basically use the magnitudes and predict the redshift, and now we can also take another step showing the whole image. So it's another example. This is the example I showed on the first slide, where we took these 100 million galaxies and actually using machine learning techniques created that mass map. So the bright regions are the overdensities, dark underdensities, and that's what Private Eye made of that. That's their joke. But the point was really also to see profiles. So I'm nearly there. Here you can see peaks and voids, and it can go to the next step of actually, rather than compressing data into power spectrum, to show many, many simulations and to predict the cosmological parameters. So, and you can also tell where they come from on the sky. So that's really the hope. Just to say that the young generation needs new training, and we have this center at UCL that we started 6 years ago that students do prepare for a dual career, both in astronomy, particle physics, and in industry, and they spend 6 months in industry, and we already got 15 theses or so coming out of that. That's my summary. I think it's an exciting era ahead, billions of galaxies. I think point number one, cosmology can no longer be done without machine learning, but point is, we're still waiting, We've got hammers, we're interested in nails, and it would be nice to see something really where you can say proudly, using machine learning, you change the world. And I'll stop here. Thank you very much.
Yeah. Many thanks, so for giving that talk, summarizing the status of cosmology as well as how machine learning can be used. Let's have some questions. We have some time for questions and discussion. Yes, Jasjit. Can you wait for the microphone? Oh, there is.
Oh, okay.
I'm so sorry.
No, I think I can.
Okay, you can shout, I can repeat the.
Yeah, it's come
Okay.
up. Yeah. So thank you for the nice talk. I wanted to go back to the point you raised about when to stop. Isn't there, see, if we have a theory which has been tested many times and it has proven itself to be consistent, and then we have a number we can live with. But if we don't have a theory,
Right.
if we are not confident in the theory, then I think we do have a case of going on and trying to pin that down.
Yeah, so that's one argument.
And I feel that here, that
Yeah.
it does fall in that category.
It could also be that the theory is wrong.
Yes.
So, that actually if you do more, eventually you'll hit a new discovery,
Right.
which to some extent you can say the lambda example illustrates that.
Thank you, Jasjit. Any other questions?
There's one there.
Oh, yeah.
How blind can having a theory make one to what the data is telling us?
Would you mind repeating it?
No. Can the fact that we have a theory make one blind to what the data is telling us?
Yeah. No, well,
To what
it's
extent?
look, it's an interesting philosophical question, right? We can only look at history, right? Only look at history. That sometimes a theory leads, well, I would put it this way. Okay, it's a long discussion, but to keep it kind of short, I would say the following. I think it's good that there is a theory because it helps to focus the mind. So all these surveys probably would not get funding without a question about W. So, and also you optimize them, so you get better results in a way from the instrumentation, the software. But then it's really a question, you can just be on the wrong track. That's what you're saying. You could just, theory could just, and you just continue and continue. And then who knows? I mean, there are examples of both cases that when there are anomalies, it's either you just have to put Neptune there to fix the problem, or you have to change the whole theory, like in Mercury. So I think we have to keep an open mind and go back and forth.
Thank you.
Paul, there's a question.
Ofer, thank you so much for this very good tour of the horizon for cosmology, and seeing what DESI and what the Dark Energy Survey have added. I wanted to ask you a somewhat broader question. You talked about the Hubble tension, and you made it sound mostly like this was maybe one's right and maybe the other one's right. And, we should sort our way through the uncertainties and the errors.
Right.
Well, of course, but you went kind of quickly over the question of what if it's real, and what would be the implications, and do you think that there's room for new physics, you know, early dark energy or some other aspect of things? So I wondered if you could expand a little bit on that topic.
Yeah, so what you're asking is, imagine both are correct. Let's just do the exercise. Imagine both are correct. So then people, for example, talk about dark energy that changes with time. That you can fit, because the difference is, of course, the CMB value comes from very high redshift, 1,000, and the other one comes from nearby. So if you have something which goes in between. So there's a review article, which I think has got like 100 models that look at exactly that question. I'm sure you know that paper. I get the impression it's not so easy. Somehow, it's not so natural. I'm sure if you have enough free parameters, you know, to go to redshifts, you get something. But it's, you know, it's not so easy, not so natural. So yeah, I mean, I think it's good. You know, it's good that it stimulates people to think about it, because maybe there is something. That's if both are correct, but you know, it could also be that both are wrong, right? In principle. And each comes with a different, I mean, we know it well, right? CMB, it's relatively simple physics, but it's a package. It's a package deal, which includes components we understand. And the CEFI is relatively, you know, straightforward. It's direct measurement, but messy astrophysics. So, yeah, it's all very interesting. Yeah.
It's also great that these things are done in a blind manner these days.
Yeah.
So without taking a look at what the other analysis is telling us. And, before you're sure about all the systematics, especially in this game where the systematics are starting to dominate, I think we have to worry quite a bit about these biases.
That's right.
Any other questions? Good. You have one more? Let me go there first and then come back to you.
So how come errors determined by gravitational waves silence are higher than Planck or Rice and others?
Well, it's because if you think the first one, the bright is based on one object. Okay. Plus there are a few nuisance parameters in it, like the peculiar velocities. So that's why you get. I think there are forecasts, lots of papers in the literature, that you see what happens with 100 and 1,000 and so on. I'm sure you've calculated this for the facility you're developing here. And with the dark sirens, there are more of them, but each of them is very uncertain because you have to, you don't know if the object is in that galaxy or that galaxy. So you integrate, you kind of put a probability over thousands of galaxies. That's the way to think about it. Yeah. As suggested, by the way, by Bernard Schutz back in 1986, 86, yes.
Yeah. Indeed.
Yeah, no idea.
Yeah, so all these questions and discussions are interesting. Unfortunately, we'll have to move given the time constraint. Of course.
I would like really just to apologize that I have to leave in a few minutes to catch an airplane. It's really a shame, because I would have loved to hear other talks and to discuss.
Thanks a lot for coming here.
I appreciate that. Thank you very much.
Thank you.
Great. Of course. Oops.
So the next talk is going to be by Prateek Sharma, Professor Prateek Sharma. He did his PhD at Princeton University and his postdoctoral research at the University of California, Berkeley. He is currently, of course, a faculty member at IISc in Bangalore. Pratik's research interests are concern the baryons in the circumgalactic medium. He uses hydrodynamical simulations in order to address these issues. And I want to congratulate Pratik again for the award. And we look forward to hearing from you about the multi-phase circumgalactic medium. Let's see if I can get this talk up for you.
Thanks a lot. First of all, I'd like to thank the ASI and the selection committee for giving me this honor of presenting this, getting this award. And this award is not possible without the contributions of students and collaborators, and I duly acknowledge their contributions. So I'll get started. So I'll be talking about atmospheres around galaxies. And so the title is Multi-Phase Circumgalactic Medium. So circumgalactic medium is referring to these diffuse atmospheres around galaxies. So this is a brief outline. Okay, it's working. Okay, so I'll just give a brief introduction, some observational probes of the circumgalactic medium, and a couple of problems that we have been working on at the end. So this is the context. The structure in the universe forms because of the seeding of density and temperature perturbations in the early universe. These perturbations grow nonlinearly because of gravitational instability, and you form this large-scale structure that you see in the shape of these filaments and pancakes and nodes where these filaments are meeting. The most massive nodes are known as galaxy clusters, but even smaller galaxies are at smaller nodes. These are sites where normal Milky Way-like galaxies are formed. So this is a schematic of the CGM. You can actually approximate it as a spherical model for the 0th order. And so you have this very diffuse dark matter dominated halo, but there's also about 20% of baryons within these halos, consistent with the cosmological fraction of baryons. And there's a lot of action going on right at the center where there is the disk of gas and stars. But the most interesting thing and the topic of this talk is this diffuse baryonic atmosphere around galaxies, which contains most of the baryons associated with these halos. These are typical numbers. The size of this halo for Milky Way is about 200 kiloparsecs. For more massive systems like clusters, it's about a few megaparsecs. The CGM is sort of at the interface of intergalactic medium. This is IgM filament seen in dark matter simulations, but you have baryons which are sort of more or less following this structure as well. This is an example of the CGM seen at a very, very small scale. So if you zoom in the disk, some starburst galaxies like this poster child of galactic outflows called M82, Messier 82, shows multi-phase galactic outflows. So this is the HST image of the stellar disk of the starburst galaxy. In blue, we have Chandra X-ray emitting gas observed by Chandra. And then so this reddish is dust emission seen in Spitzer. So this is a composite image. And you see these very close to the disk of the galaxy. So this is the disk of the galaxy right there at the center. You see these multi-phase galactic outflows as traced by these different tracers. So this picture tells us that there are a lot of roles that the CGM plays. This is the reservoir of mass and energy. This baryonic halo grows because of accretion of matter brought together by gravity of the central halo. And it's regulated by this activity at the center due to starburst or due to supermassive black hole. So this is sort of the 0th order picture of galaxy formation for you. Now, I'll motivate why should we study the CGM. And there are various reasons for it. As I mentioned already, that most of the baryonic matter lies in this diffuse and almost imperceptible atmosphere of galaxies. And there are a lot of players happening, participating in the process of galaxy formation act in this phase. The other thing to understand is that the CGM is very diffuse. So if you quantify it in terms of delta, delta, which is delta rho by mean density of the universe, these structures are not as nonlinear as stars. Stars are like 24 orders of magnitude denser than the mean density of the universe. These are more like, 10,000 or so. And we have a lot of observational probes which probe various aspects of the circumgalactic medium, as I sort of briefly showed in that image of M82 outflow. And we want to understand the trends of the CGM properties with various things like the halo mass, environment, and redshift. So, the question is, how do properties of how do galaxy properties scale with redshift and halo mass? At some, the universe started with tiny density fluctuations, and these fluctuations became nonlinear and produced the structure that we see around us. So CGM is an example of such a structure. So this is a brief outline of various probes of the CGM. So this is a schematic map showing how, so here is a bright background source like a quasar, and this is our Hubble Space Telescope, the Cosmic Origins spectrograph, which is sort of is staring at this quasar, which is a continuum source, and the ions in this CGM embed characteristic spectral absorption features in the spectrum, and that is how the observer is able to infer the presence of various ions, the temperature and density conditions in the CGM. But as I'll mention next, it's a little hard to interpret these observations because modeling the plasma which produces these spectra is non-trivial. Now you can actually, so this is absorption-based study, so you cannot make a map of the CGM using these, you can get statistics, but you cannot make a map. But we can sometimes make maps of the CGM. For example, as shown here, this is a similar thing as the M82 outflow, which I showed previously, here on a larger scale. So this is an oxygen-2 emission map seen in a nearby starburst galaxy. Now, our Milky Way is also surrounded by the circumgalactic medium, and all sight lines which we observe external objects from pass through the CGM. So one can actually look at something like X-ray emission from a survey like E Rosita. So E Rosita has looked at this patch of the sky, which is sort of relatively away from the mid-plane, and tried to see the signature of the CGM. What is shown here is a region called the E-FEDS, E Rosita survey early data release. What it shows is X-ray surface brightness map. And from this you can actually see that there are overdensities and underdensities in the CGM. So this circumgalactic medium, as seen in X-rays, shows density perturbations. Okay, and that's sort of part of this complexity. People have also studied the X-ray emission from other galaxies by stacking surface brightness of galaxies. This is an example. This was done from Rosat. Now, there are newer probes of the CGM. For example, the fast radio bursts. I'm sure most of you have heard of the fast radio bursts. So fast radio bursts are like pulses, and their arrival time, they arrive earlier at higher frequencies. So by looking at this arrival time versus frequency plot, we can actually see how much column of electrons does the pulse go through as it comes from its source. So this basically provides us the electron number density integral along the line of sight. So this is a cleaner probe compared to that. Both of them are sort of absorption probes, but this is cleaner because you're getting electron number density along the line of sight. And electron number density is almost equal to ion number density. But a particular ion can be overabundant and because the ions, the metals are extremely rare, right, compared to electrons and protons. So if you can get a handle on protons, it's easier. This is FRBs. The other probe is something called the Sunyaev-Zeldovich effect, which essentially is the distortion of the cosmic microwave background, which has a typical characteristic signature which can actually be modeled, and it gives us the integral of pressure along the line of sight, electron pressure. So these probes are relatively new, but they are also clean. So, we are looking at everything that we can put together to understand this complex system. Now I'm this was my introduction. Now I'll be starting with a few of our works that we have done in this business. So the question is, why do we have multi-phase gas? So as I mentioned, these CGM absorption studies of quasars show signatures of ions which trace a large range of temperature and density. So all the way from 10 to the 4 to 10 to the 6 Kelvin. So what it means is that the atmosphere is full of all sort of densities and temperature. Okay, so an analogy that I have in my mind is something like clouds on the earth, right? Terrestrial clouds, right? It's made of tiny droplets, and most of the area of the sky is actually covered by clouds. In the same way, even small amount of mass in these diffuse atmospheres can actually cover a large amount of area, so we can actually see them in typical quasar absorption features, okay, even though they have less amount of volume and mass. Okay, so let's start. So this is something called the cloud crushing problem. It's a model problem to study the circumgalactic medium. So what's the problem? Let me just sort of describe it. So you have a spherical cloud, and you have a wind which is blowing on this cloud, okay? So there will be strong shear at the surface of the cloud, and that shear will try to mix this cloud in this diffuse medium. Okay, this problem has been studied for like decades. So and why do we take this as a model problem? Because the CGM is multi-phase. There is gas at a continuum of densities and temperatures. So if you have dense cloud and low density wind, it will mix because of turbulence, and it will produce continuum of densities and temperatures. So if you do an analysis of this problem, there are some important dimensionless numbers like the density contrast, chi, which is the density of the cloud divided by the density of the wind, and the Mach number, velocity of the wind relative to the sound speed in the hot diffuse medium. So if you do all this, the theory tells us that this cloud, because of Kelvin-Helmholtz instabilities at the interface, should get mixed with the diffuse wind on a time scale which goes like chi to the 1/2 times the crossing time. Typical value of chi is, say, 10 to the 6 Kelvin divided by 10 to the 4 Kelvin, which is about 100. So the denser cloud is about 100 times denser compared to the diffuse atmosphere. So this is the cloud crushing time. Another time scale that you can actually define is the drag time. So you have a cloud and you're blowing wind on it. What is the time scale over which this cloud will start moving with the velocity comparable to the velocity of the wind? So that's the drag time. And that goes like chi rather than square root of chi. So what it means essentially is that the clouds will get mixed before they can be dragged. So the question is, if some source is blowing these clouds out, what this calculation tells is that these clouds will just dissipate locally rather than being uniformly spread out throughout the CGM. Okay, so this was a big puzzle. But over last 5-6 years, there's some progress on this puzzle. And what these graphs actually show it illustrates a way towards the solution of this puzzle. So I'll actually walk through this a little slowly. What is shown on the left here is dense mass. How much is the mass in the dense cold phase inside a box as a function of time? There are these curves which all fall down. So what it means is that the dense mass in the box goes down. And this is what we expect because of turbulent mixing and shear. But if you include radiative cooling, which is actually an important process in the CGM, what happens is the nature of this curve changes qualitatively. So the clouds start reducing their mass because of mixing, but then they suddenly pick up growth. Instead of getting disrupted, they start growing. Okay? And this has important implications. They start growing because it produces a lot of mixed gas, which has a short cooling time. And that mixed gas with short cooling time can cool and contribute to the mass of the dense gas. So this is important to sort of keep in mind that with radiative cooling, if certain conditions are satisfied, you can get growth of clouds instead of destruction. What this shows, the figure on right shows, is velocity difference between the cloud material and the wind material as a function of time. And the same curves are shown here. And you see that, irrespective of whether the cloud grows or gets destroyed, the nature of these curves does not change, unlike on the left. So basically, this is a way to get around this problem of how to keep these clouds even with this blowing winds, even with this large shear. And this was actually considered a big breakthrough. Our group has been working on this, but there are also other groups which have actually contributed to this quite substantially. And this was actually quite an exciting thing. So here is a movie that I'll be showing of the same problem. Those graphs as a function of time were based on such simulations. So here are some of the parameters, but I'll just play the movie. So what it shows is number density snapshot in the midplane. And if I play it, so the thing to notice is that that the cloud starts, it gets mixed, but suddenly all this mixed gas cools in the tail of the cloud. And you can actually see that the density goes down, and then suddenly it sort of starts accumulating back in the tail. So this is what is responsible for this behavior of first dipping, the dense mass dipping, and then growing later on. And this is absolutely important because this is how we can actually explain this, all-pervasive, multi-phase, multi-temperature gas in the CGM. Now, so as I mentioned, the introduction of cooling in these simulations changed the physics qualitatively and in the direction that we want to go to. So it's important to know what I'm talking about when I say radiative cooling, right? So all plasmas and atoms and ions can cool because of two-body processes like Bremsstrahlung cooling, or a hit with an electron can excite an atom, and then it radiatively de-excites and emits an electron. And since these CGM is so dilute, it's optically thin. So you can actually model radiative cooling in a simple way where you just sort of introduce it as a loss function. So this is something called the cooling curve or the cooling function as a function of temperature, and it characterizes the radiative efficiency, the efficiency with which a plasma cools as a function of temperature when it is in collisional ionization equilibrium. We don't really have to look at all these lines. The thing to keep in mind is that this is 10 to the 7 Kelvin. Almost all the plasma is fully ionized. So the plasma cools by Bremsstrahlung cooling or free emission, but at lower temperatures, different ions like oxygen ions, iron ions are very efficient at radiating. So this atomic physics curve actually governs a lot of galaxy formation that we were talking about. Okay, so this is just useful to keep in mind. The curve, these different curves are for different metallicities, and the CGM is like somewhat lower than the solar metallicity. But the point is to notice that this intermediate temperature gas. So x-axis is log temperature. Intermediate temperature gas has more efficient cooling. This is another movie which shows, actually this is a single snapshot in time, and this is a 3D volume rendering of the cooling time. And what you're seeing is you're looking at this cloud from different directions. There's some camera angle. And the purpose of this is actually to show the structure of this multi-phase stuff. So it actually looks like a terrestrial cloud. If you go up in an airplane, you actually see these extremely fractal-like surfaces of clouds. So this sort of gives you a visualization of that. That's why keeping this terrestrial analogy is a good in mind is a good idea. Now the question is, how do you get these clouds in the first place? One of the ways you can actually do that is by blowing, as I showed you in M82, Messier 82, this galactic outflow, there are supernovae going off, AGN going off, which sort of puts a lot of energy in this ISM, and sometimes it can actually lift off dense pieces of the ISM and flings it in the wind. So you can actually produce these seeds initially. Now the question is, what happens later on? So this problem of clouds in an outflow is somewhat different from the problem of clouds in a uniform background wind. Okay, and this is something that my student Alankar Datta is doing. So this is something new. What we are doing is simulating galactic outflows, hot outflows. This is a standard model for outflows, and then putting clouds in this. The reason we want to do that is because as the cloud moves out, it's sort of going into a different ambient conditions. This is a plot of density as a function of radius along the wind. So the density falls as the cloud is pushed out. So eventually, you can actually see this visually here, that as you go out, the clouds sort of become rarer and rarer. Okay, we are sort of studying that right now. This is actually showing a simulation of this process. The same density cut. This is dense thing. The cloud starts to grow because of cooling of this intermediate temperature gas. But later on, and you can actually see the long tails of like intermediate density temperature gas. So right now, cloud was growing, and in fact, we are actually using a moving grid to track this mixed material. And eventually, what happens is this cloud actually stops from growing. So I actually think I need to move on. So this is sort of the last part, which is a little more analytic modeling of the circumgalactic medium. Actually, Mukesh, who's here at the ASI meeting, is giving a poster on this. If you're interested in this topic, you should visit him for his poster. So what's shown here is the magnesium-2 column density. Magnesium-2 is the tracer of 10 to the 4 Kelvin gas. Okay, singly ionized magnesium, magnesium-2. And this is from a cosmological galaxy formation simulation called TNG50. And what it shows is sort of a column density map of MG2. What you see is that there are a lot of sight lines which are sort of empty, but there are other sight lines where there is a lot of cloudy stuff in the foreground. So we thought, can we model this using some sort of phenomenological model? And what is shown here are the PDFs, probability distribution functions, volume PDF. So in orange, we show the amount of volume occupied by gas at different temperatures. So x-axis is temperature, y-axis is PDF. And what you see is from these complicated simulations, if you sort of fit it with 3 log normals, the fit is actually not that bad. So we take the volume PDF from the simulation, fit it, and then have a predictive model for the mass and emissivity PDF. And, comparison of dashed and solid lines is not that bad. It gets the qualitative features right. And so the nice thing about this analytic model is we can actually do a lot of diagnostics. We can calculate a lot of things. For example, if you're interested in column density of a particular ion, all we have to do is find from this PDF the number density as a function of spherical radius, and then do this Abel integral along the line of sight. So these are some comparisons with observations. So this orange data is oxygen 6 absorption from this COS survey, and the solid line orange there is a comparison. The cyan points are for Mg2, which is a lower temperature tracer of the gas. And what you can see that there's a much larger spread in oxygen. You know, these upper triangles pointing up are lower limits, triangles pointing down are upper limits, and you can actually see there's a large variation in the data, which basically what it is suggesting is that the colder phases are more clumpy. Some sidelines don't have any clouds, the other sidelines have like very dense clouds. So we can do other observables, for example, X-ray emission spectrum and dispersion measure and so on. So this is the summary of my talk. I hope I have convinced you that the circumgalactic medium, which is a major baryon reservoir associated with halos, is a crucial player in galaxy formation. This is where interplay of cooling, feedback heating happens. And then I talked about these two projects, the cloud crushing problem, growth of clouds with and without winds, and modeling the circumgalactic medium using a PDF, a probability distribution function approach. With that, I thank you. Thank you very much.
Thank you, Pratik, for this interesting talk on the circumgalactic medium. So, any questions for Pratik? Yeah, there's one there.
Hi Pratik, it's really nice of Mahavir here.
Hi, Mahavir.
So, it's about the CGM. So, what I got, that is it a common understanding that it's dynamic and that was specifically an outflow?
Yes, so it's not all CGMs need to be very starbursty and outflowing. Okay, so one way of producing clouds is the throwing out of clouds from the center, but the IGM filaments themselves, then there are satellite galaxies whose atmospheres are stripped. So all these complicated cosmological processes can also seed clouds and produce multi-phase CGM. In fact, on a volume average sense, that has to be a bigger contributor because the galactic outflows are tiny in terms of the volume.
Thanks.
Dibendra here.
So Pratik, I assume that substantial fraction of this medium would be also in the plasma state, right?
That's
so
right.
Mix of plasma and dust. I'm wondering if you worry about that coupling and whether magnetic fields play a role in structuring the outflows and maybe
This is an excellent question, actually. As most astrophysical ionized and even non-ionized gases, this is also a plasma. The thing is the quality of observations is not quite there yet to explain rotation measures and things like that, but people are getting there. Some of these CGMs have been observed through Faraday rotation, so at some point we'll have to get there. Also, there are filaments in intracluster medium where you can actually image low temperature 10 to the 4 Kelvin phase, say in H alpha, and you see almost things which look like low beta solar prominence like filaments.
Hi Pratik, thanks for the nice talk. So I was wondering whether you have an observable that is directly coming from the radiative transfer that you can directly compare as like what you have shown for one emission. So is this something that your model also?
Right, so as I mentioned briefly that these are extremely diffuse atmospheres. So a lot of radiative transfer effects are not that important, but that's not true for all ions. For example, Lyman alpha, there's so much hydrogen there that radiative transfer is extremely important for Lyman alpha. Okay, so there are problems here where radiative transfer will be important, but I have actually not looked at, our group has not looked at that. But for most other ions, it's fine.
Pratish.
Yes. Anand here. I think to have an average picture of what is CGM from an observer's perspective, I don't think the poster child is a good example. Because as Mahavir also pointing, and you answered, it's just few millions of years that outflow happens and this gives a beautiful picture. But what should we focus actually is the H1 picture, that will be better. Because the extraplanar feature in H1, they rotate slower than the disk. And how far it goes, we really don't know. So that is, so for millions of years, several galactic rotation, that is there. I think that is a more direct picture.
I agree with you absolutely that H1, like high velocity clouds in the Milky Way halo, and other like H1 features in nearby galaxies will be very important to look at. So I just had a handful of observational probes, but that page can easily be doubled.
Hi, one last question.
Where is the question?
Where is it coming from?
Where is the question?
Okay, here.
Okay, here.
First of all, thanks for the nice talk. Had a good overview of the whole CGM problem. My question is a kind of a two-part question. So the radiative cloud crushing problem, I gather it might require enough resolution to model it properly. So I was thinking, how does it depend on the resolution of your simulations, and what implications it might have for galaxy formation that follows because of this problem?
Right. So you're raising a very, very important point that what resolution is enough to simulate these processes. And the answer to that is, whenever you do a simulation which does not include explicit dissipation and conduction, even if you do turbulence, you don't get you don't get converged answers. You get, if you have a higher and higher resolution, you see finer and finer features. Okay, so one has to actually do a DNS in order to get converged answers. But particularly for the multi-phase part, there are also length scales in the problem. Without cooling, there are no length scales. In Euler equations, there are no length scales. But with radiative cooling, there are physical length scales. And people say that you have to resolve extremely tiny scales like 10 to the minus 3 parsec or something like that, which I think is not feasible. So I think we need a fresh perspective on how to incorporate these in a subgrid way so that these effects are incorporated, but we can still do simulations.
So more questions can be done later. We thank again for this wonderful talk, Pradeep.
Thank you very much.
So our next speaker is going to be Arvind Paranspe. Arvind has a master's degree from Pune University, but he has helped blossom the science popularization program at IUCAA. He led it for almost a decade before moving on to his position as the director of the Nehru Planetarium at the Nehru Center in Mumbai in 2011. He has had an amazing journey from an amateur astronomer to a professional one, during which he has also inspired so many others to take on science along with him with his science popularization activities, as well as his sky watching sessions in astronomy, some of which I have personally benefited from, especially coming from a rural area in Maharashtra. So I've enjoyed reading also numerous of his newspaper articles and articles which came in leading periodicals. So congratulations, Arvind, for a well-deserved Zubin Kembavi Award, and I would request you to deliver your talk.
Thank you. Let me check, it's working, yeah.
It's working.
Thank you. Thank you so much for introducing me. I also would like to thank ASI, then the selection committee, and that unknown person who nominated my name for this award, and Asha and Ajit Kembavi for constituting this award, because it means a lot for people like us. Friends, I'll just briefly talk about my little journey. I mean, my beginning was quite humble. Joined as a technical assistant in the laboratory, photographic laboratory of IIA Bangalore, and I started working from there. So when I was in first year of BSc, I was doing a lot of laboratory photography at home, developing films, etc., and that culminated in participating in the total solar eclipse of 16 February 1980. One of our team members, we were all amateurs, so one of our team members was Madan Rao, if you would, some of you might remember or know him. So that is how it happened, and total solar eclipse took away a lot of my grades, and so it was but natural for me not to get into MSc. And I desperately needed a job. And then I went to Professor Venu Bappu and Professor Bhattacharya. And I showed what photographic work I was doing. And well, I ended up. So actually, at one point in time, Bappu asked me, where did you learn this darkroom techniques? And so I had to tell him that Dr. Tushar Prabhu had shown me, because as an amateur astronomer, I used to go and work in the same laboratory. Well, that was the start, and it was a very interesting journey there, because my job mainly was to make 35 mm slides for director and deputy director, etc. That is Professor Bhattacharya, Professor Venu Bappu, and some others. And then I also had developed this very knack that, in those days we used to have 35 mm slides, not like this, what we have today, that you were to load the slides in a tray. And I could just see for a fraction of a second, and I can put, because slide can be put in 4 different ways. So I could do that. And this gave me entry into the technical session or popular lectures of at IIA. So that was it was a kind of a dream job for me. But Professor Bhattacharya also allowed me to do a lot of experimentation. And that experimentation part is that we used to have mixing chemicals to do take out better images from the slides and so on. And I must tell you one small thing, that there was one chemical called potassium ferrocyanide. So the moment you hear about cyanide, you have that you know what we are talking about. What potassium ferrocyanide is completely non-poisonous, because if at all it was poisonous, Anupama here and myself, we wouldn't be here, because after everybody went away, some of us will get together in the laboratory, photography laboratory, and make tea in the beaker in which I was mixing the chemicals. Okay, so now that was very interesting. And one of the things which I remember at IIA is when the Professor Zednik Kopal, he came and delivered series of talks. And I really can't forget those, and how passionately he talked about John Goodricke, who was an amateur astronomer and who started the variable star astronomy. This young man who was dumb and deaf died at the age of 21, and he was actually nominated for FRS, but he couldn't go because he was already he was not well. And that sort of led me into interacting with amateur astronomers and do telescope makings and so on. And then what happened was that I shifted to Pune. And Pune, again, my job was, Professor Kemba is here, for making slides and PowerPoint presentation, because by then PowerPoint presentations came. And I learned these techniques of making the PowerPoint shows. So when I wrote this, I really had no time to make the PowerPoint presentation, but when I wrote some of these notes, one point which I wanted to talk to you about was so very nicely illustrated by Pratik just now, and that is that have a nice picture, slide or your PowerPoint presentation with white background, bold, nice black letters, and it goes very well. Now, please remember, I'm only talking about giving public talks and not technical scientific talks. Technical scientific talk, everyone knows what generally the speaker is talking about. So these are the thing that what you put on the your screen, what topics you deal with, how sequence goes, and that was very interesting to me, making this outreach lectures. Actually, for a certain period of time, as long as I was at IUCA, I made large number of PPTs for Professor Narlikar. Now, having said this, I would like to tell you, as we saw in the morning, Deepankar had said that almost 50% people are youngsters. So soon, you will be probably talking to the press, you will be giving public lectures, and there are some do's and don'ts that I thought I should mention about, and that is that when you talk to the public, try to be as simple as possible. Now, same thing about Pratik's talk also, that of course his was technical talks, a lot of equations, graphs and all that were there, but avoid graphs, equations, have only 2 or 3, maximum 4 points on your slides, one after the other. That helps communicating to the public. If your slide is cluttered with large number of data or large number of small things, one thing is the people start reading what you have written next. Okay, their attention is diverted, and you also might get lost in that. So try and keep a number of points on your slide to say about four, but definitely not more than that. On this topic also is a point I would like to share with you, and that is the color. As he has done it very nicely with the white background and black color, but I have noticed that if you use cyan color, which looks so good on your computer screen, may not get projected on the big screen because situations might be different. Here most of us are playing on our home ground, but when you give a public talk, you don't know who is, someone is organizing it, but what kind of setup they have, what kind of auditorium they would have, and therefore your talk, as long as you keep it to black and white, it works very well. Thirdly, the point which I have suffered myself quite a bit in, that is when you carry movies and sound in those your slides, because sound bites. Because if you go to school or some amateur astronomers association, they may not have the kind of setup that professional organizations have, and many a times sound and movies do not play, and then you start looking around for something. Then also comes a point that when you give a public talk, normally you would go to the internet, take out certain information, and then give your talk. But in public talk, maybe you have a copyrighted material. So I've seen Professor G. Srinivasan, when he came to give a talk at Nehru Planetarium, he actually asked us to delete his PPT from our computers. Well, there are many points like that I would like to tell you. But let me just go to the second point, is the press releases. Professor Narlikar has been extremely good at drafting press releases. So, and I remember whenever I have made a press release for him from IUCAA, the press release Times of India would print out completely verbatim, just as it is. And then in competition is the Indian Express. So Indian Express knew, so Indian Express would make some small minor changes here and there, and they print it. So what is so important about making press releases? See, in technical talks, scientific talks, your conclusion comes in the end. In press note, it should start with your conclusion, or what is the result. That bold result, that information is what the press people would catch. So you start with that. Thereafter, you give a little bit information about the instrumentation or whatever you have done, and finally add people whom they can contact to. Of course, after saying all these things, then you can have one or two pages where detailed information is given. So this works very well. Just 3 or 4 paras about your research or discovery, and thereafter you can add supplementary information. Now, one thing we have also noticed, and my friends in press told me, is that give a press release on Fridays, because the political situation becomes dull on Saturday, Sunday. So Monday they have a lot of space, so they can print your story, which is, this is what we call it, story. So they will print your story. So unless it is something path-breaking, something very big, avoid and give your press releases on on Fridays. And then I think I would like to tell you one more thing about the public talk. You see, there was a time when whatever talk you give, maybe you have talked about Tycho Brahe's instruments or Jantar Mantar or something. The first person to ask question is, sir, what is a black hole? I think most of us have suffered. So then as an organizer, I would stand and say that, look, this talk, you should not ask about black hole. Now these days it is dark matter and dark energy. Now we, the Planetarium Society, we have a group, we meet very regularly. So one thing that came out was that when someone asks this question, and of course we used to get very irritated, but now what we do is, moment someone asks such question, oh, that's a very good question, but I will talk to you later, send me email or talk to me outside. That person is not going to come back to you again. So that is what it happens in the public talk. And well, let me see if I have missed out something on the press releases. Yeah, another point that I would like to share with you, both professionals as well as the youngsters, seniors and youngsters, is that when press person comes to you and takes down the notes, okay, watch very carefully what he or she is doing. If the pencil stops working, you know that person is not interested. Just forget it and go to the next story. I mean, the next thing that you would like to say. I've noticed that press person comes to you, you have a press conference or a press meet, or someone comes to you and talk to you about your work, and then you are talking about, you passionately talk about something and something, and then you find that all of a sudden that writer, the reporter has stopped taking down the notes. You know that he is not interested, and whatever you are saying will not come into the paper tomorrow. And on this topic, in the newspaper thing, yesterday's story is already obsolete, so don't worry about it, what happens. So only thing that is important is what happens today, and yesterday's thing is obsolete. And lastly on this topic is that press remembers, press honors embargoes very well. So if you want something to come out, something not to come out before certain date, just write embargo. All press people will honor your embargo. Well, lastly, I would like to share a little bit about my venture into conducting star parties and all that, and I will end with that. I'll tell you 3 stories about it. When I came to the planetarium and we started conducting star parties, it's fun. It's always a fun. People get together close to slightly before sunset. It's a big ground, and then you organize first sky watch. After that, you do a little bit of lectures. Then sky gets dark, and once the sky gets dark, then you allow people to see through the telescope. So just before the pandemic, we had conducted one star party, and then initial talks and all that is done. And the sky was really good that night. And as the light went on, the sky was seen. And someone commented that, oh, this sky looks like a planetarium sky. So that's the change. I mean, the planetarium is supposed to show the real sky and that. We meet a lot of people with a very difficult situation. One of the situations is, or you see that often when you show Saturn, there will be one person or the other who would do prayer before putting his or her eye to the eyepiece to see Saturn, and then she'll mutter and thank you and etc. That happens. So we had one person visiting our planetarium during some total lunar eclipse. It was late in the night. Mumbai sky was completely cloudy, and around 8:30, 9 o'clock, people started assembling, and this person, okay, I'll say that so-called the high society. So she came and said, we said that, look, sorry, we can't do because sky is cloudy, and she started arguing that, oh, yours is an international institution. And I started thinking whether she has heard about TIFR or not. So institution, and you should be able to show. And she started creating a little bit of mess. But that because people had come, so we had to honor them, having come all the way. So I just got them inside the foyer and said, okay, you please sit and we will talk about the solar eclipses, lunar eclipses, something. I will entertain you for about half an hour and then we can go home. And those who want to go home, of course they can. Sky was not likely to clear up. So she said that again. And at that point, I just said, ma'am, what you say might be correct, but if you show me a place on this world, on this earth, where a telescope is put and you can see the eclipses above the clouds, I will this is my planetarium, so I will entire planetarium I will donate to you. So some people laughed and then she left. So such situation we meet quite too often. And let me end with a very funny incidents that we had many years ago at Ayuka. I was working where I was working. Professor N.C. Rana, Professor Shyam Tandon, and myself and some other one or two people, I don't recollect those. So we had gone to a place called Latur and conducting this introductory school on astronomy and astrophysics. And it was all planned, and we had taken a telescope, and I'm just trying to tell that if you're showing the sunspots, so what can happen. So we had taken out a 3-inch telescope. By the way, it's a very wonderful telescope which was made during the arrival of comet Halley at IIS. Somehow it did not go through very properly, but it's a beautiful telescope. So we made the attachment and showing sunspots in the classroom, in the lecture hall, everywhere. We told people not to look through the eyepiece. The sunlight is too strong. You might lose your eyes. It's eyes on the spot. Don't do that. And when you do such a thing, you are always concentrating. I mean, you are one attention when you talk to the public, when you are showing the sunspot. You are always, what I should say, looking at your what your public is doing to the eyepiece, close to the eyepiece. So it so happened that as I was talking about sunspot, one young girl, say probably final year BSc or first year MSc or say, something like that, she came and she actually started looking through the eyepiece. She was about to turn. That eyepiece was put at 90 degrees. And instinctively, I pushed her away. She did not fall down or anything, but pushed her away. But that was a grand insult to her. That and I was also quite young at that time. Okay, so if at this age, if I push, probably nothing serious will happen. Yeah, I know, I'm done. So I pushed her away. And in about 2 hours' time, she was a daughter of some mukhia or some important person from that city. So she came with her father, and father came and started shouting at me and say, "How did you touch my daughter?" and so on and so forth. And of course, the situation was little tense. So after he said whatever he wanted, I coolly stood there, listened to him, and after he was done with his team, then I said, "Sir, please remember that everybody I had told not to look through the eyepiece, and your daughter was trying to look through the eyepiece, and she would have lost her eye immediately." Now, this Mukhia's mind was racing much faster than the speed of light. He went about 2 years ahead, and he realized and he shouted at her, "What would have happened if you would have lost your eye? I would have to pay so much of dowry to get you married." Okay, so with this note, I thank you for listening, giving me a chance, and I am really grateful to ASI to give me this award. I'm really grateful. Thank you.
Many thanks, Arvind, for this wonderful talk and your experiences relaying them. Any questions?
We are all hungry.
Yeah, all hungry.
Yeah.
I'm sorry? What about the black holes?
Very good question. I will ask you. Write to me. I will tell you later.
Okay.
Okay.
So if not, then let's thank. Oh, there is one. Okay. Sorry.
Yeah, I mean, that was a really nice talk. I was wondering, you've done this science popularization for almost more than 2 decades now. Do you find 4 decades? Wonderful. So do you find that there has been a change in the mindset of Indian common man regarding such superstitious events like eclipses, or whatever, the conjunction of Venus and Saturn, or whatever? I mean, have they changed the attitude towards astrology?
Okay, I'll give you one nice example for that. When we had this total solar eclipse of 16 February 1980, Doordarshan showed movie Guddi on television, and streets of Mumbai were completely deserted. All across the country it was like that, and I remember Professor Narlikar wrote a very sentimental letter to newspaper saying that you people have deceived me, kind of, something of that nature. Then there was this 24 October 1995 total solar eclipse which passed through Rajasthan, and believe me, all trains going towards north from Mumbai, Pune, Kolhapur, they were booked after 2 or 3 minutes of booking got open. So people did go to see the eclipse. At our place also, anytime we have any event, of course I did tell you about Saturn, but these are very rare examples. Or once in a while someone might do that, but otherwise people are interested, and even after some astrologers saying do not see, people have flocked to us. I will just make one TV related point to that, and that is that what happens is this, I can be quoted or anything, but one TV reporter told me that when such event happen and you have a television panel which is sitting, some of these astrologers actually pay and sit there and so that they can communicate to people. Whereas we actually ask them, at least you give us transport, at least pick me up and drop me back if you do not give honorarium to sit me there and talk. But they actually pay for it. But no, I think there is a very definite change among general public towards the astrology and astronomy. Thank you.
Thank you. Any more questions? You have one? Yeah, here's one. Just a moment. There's one here, then we'll come down. Okay, yeah, you go ahead first.
Sir, are there opportunities available for BSc and MSc students who have previously done some work in amateur astronomy and they can work for Nehru Planetarium? So could you talk about such opportunities?
Are you from Nehru in Mumbai?
No.
Okay, Nehru Planetarium we do not have, because it's a basically outreach kind of a place. We do not have such opportunities, but very recently I've been talking with him and others that if we can open up some activity and we can do that. And in fact, let me tell you, in the month of month of May, what we are trying to do is that we are inviting young PhD students and professors who can directly interact with BSc, MSc students or BSc or MSc and engineering students about what work they are doing and tell them how to go ahead with it. But at present we do not have, but also at some point in time at POAC I would like to suggest that today you are taking such a fantastic images, large wide angle images. So if people can be trained to analyze that data, it might be a very interesting thing to do.
Sir, my question was that if somebody has an interest, he or she is pursuing BSc or MSc, and they have interest in amateur astronomy, so they, whether they can work for Nehru Planetarium or for some amateur clubs.
Oh yeah, I'm sorry, okay, yes. No, we do invite volunteers. We do invite volunteers. Yes, you can come and volunteer. We have we have a group called DIA, that is Do-It-Yourself Astronomy. So this group meets twice a month on 2nd and 4th Saturday and interact with each other and discuss various aspects of doing astronomy, telescope observations. Like on 24th of this month, we are going to have occultation of Venus by the moon. It's a daytime occultation, but certainly you can see with your telescope if you know where to point. I think I had put this thing up on my website. So such activities, yes, of course you have chance to do that. In fact, going one step ahead, we are discussing this among other planetariums in the country.
Thank you, sir.
Yeah. So one last question from that.
My question is quite similar to that only. I want to know your vision for the space outreach as a full-fledged course or as a career.
I'm sorry. No, I don't want to say it's a very interesting question and all that, but really I do not have answer for it because we work in the popularization. Long-term thing, no planetarium has that kind of funds or to think about. I think that should be seen by the scientific organizations. But if scientific organization or institutions come to us, we can provide the platform. Maybe we should think about it. Thank you.
Yeah, thank you so much, Arvind. I remember, like, from your story about the clouds, I remember the first time I had come with you for the asteroid observations, and there were clouds. It did teach me about how patient you need to be. So thanks a lot. Thank you, Arvind. Okay, let's thank all the speakers from this particular session. And there are certain announcements, I suppose.
Yeah.
Thank you.
I take this?
Yeah. So the next is lunch, of course, which you're waiting for. Please remember the post-lunch, the first session is parallel. So if you are attending STARS ISM Galaxy, this will be your venue, the auditorium. For extragalactic astronomy and sun and solar system, it is in a different building. So when it says 1D 105 and LRC, there are the different buildings. You just walk straight from the canteen back to those places. If you are attending General Relativity and Cosmology, L02, and Sun and Solar System, L01, are basically the classrooms just right on this direction, towards the left of this auditorium. Okay, and then after the parallel session ends in 4:10 p.m., we again gather here for the tea, coffee, and poster viewing, and then the public lecture also will be in this auditorium. Okay,
I didn't do well.
Fine. There will be volunteers who will guide you. So please look for their tags, have a separate band. Okay, so I hope you'll find. Thanks. Join us for lunch. देखा नहीं? देखा नहीं?
But you did. No, I really, whatever I wanted to say. You have
Okay, the carbon building, if you go out of the auditorium, just take right and go straight. There are a couple of volunteers waiting out there, so they will guide you to go towards the carbon building. Thank you.
At all. If you just become too technical. So, I have
So after the parallel sessions, tea will be served here itself, around the auditorium.